Got the right one. All right. Hey, everybody. So, like you said, I'm Isaacs, and being here at NodeConf talking about a package manager, it really feels like I'm just coming back around full circle to the first one of these in Portland, actually. So I'm going to tell you how we spent our summer, which was making a new package manager for some reason. So why did we do that? Don't we already have package managers in JavaScript? Like, I don't know, like a whole bunch of them. I personally always found like resume stories can be a little tedious, so I will keep this brief, but this is kind of roughly how it happened, and it's a common question I get about it. So basically, a bunch of us who worked at NPM, we had really high hopes for what we were gonna do when we sold NPM to GitHub, and I think that GitHub has done an admirable job. Like, NPM still works, that's pretty cool. But, you know, reality and legacy and big company politics being what they are, we didn't, you know, things don't always go exactly how you'd hoped. So there was kind of this nagging feeling for a bunch of us that, like, I don't know, there was still stuff that we wanted to do. And we definitely felt like there was still kind of some pain points around the dependency management story. And also just no project is ever really like done, right? There's stuff that we planned on. So we kind of decided, or mostly Darcy decided, he's the guy in black and white there, that we should like do a new thing. Let's get the band back together. And so there was a logo and there was a name, and that was kind of it. We didn't really know exactly what we were gonna do. I was personally very, very suspicious that like package manager would be the answer, because like obviously that's just my bias talking, right? So we started talking to people. I gotta say, this is just a plug for what I think is like the best user research book that is available. People will lie to you like because they love you, because they don't want to hurt your feelings and tell you that your baby is ugly, but like your baby's probably ugly. So the mom test is like a set of, and I'm not like, I don't know, Rob Fitzpatrick hasn't like endorsed me or anything, but he didn't write a check. But like, it's a set of like conversational technologies for cutting past the good-natured lies. And so we did that. We reached out to a lot of people who pay, you know, a lot of companies that pay for dev tools that, you know, because we need this startup to be successful. And what we found was, first of all, there's really no allegiance or like brand loyalty in this space whatsoever. People just use whatever gets their problem solved. They had some real pain points around visibility and consistency, keeping projects up with with security stuff. We heard from a lot of people who were just like, we just turn off security, it's too noisy, which is like, okay. But you know, we do have this like weird thing in our industry where we've got these like perverse incentives to like post as many, you know, get as many things into the database as possible, because that boosts you as a security researcher. But then you got a lot of like, oh, it's like a RDOS. If you like punch yourself in the face, your site might go down. Like, all right, don't do that. But mostly for pretty rational reasons, they use the tool that works for them, which meant, well, if we could just make a good package manager, like, they'd probably use it. But yeah, anyway, like I said, I'm Isaac, like, I'm the NPM guy. Like, so the others are also NPM people. Like, clearly package manager is just like us lying to ourselves. But we did find some low-hanging performance fruit that kind of looked ripe and delicious. So what is a package manager besides a miserable little pile of secrets? Your program has dependencies, so we have to resolve those. Those dependencies have dependencies, so we have to resolve all of them. We got to fetch all of those artifacts and unpack them in the proper locations and run the build scripts. And there's like a zillion edge cases and a bunch of little overlooked details that you forget about until you are like ready to ship, and then you go, oh, right, optional dependencies. Anyway, though, it sounds pretty easy, right? So why is it so slow? These are real things that real smart, highly intelligent, highly educated, experienced people in real life have told me with their human mouths. JavaScript is a slow language. It's just your package manager has to be written in Rust or Zig or C or whatever. The problem is, the reason they're slow is that people use too many dependencies. That's the main reason, which is like, okay. Requests to the registry aren't cached locally. One fascinating example of this, I shared this story on Twitter a while ago. I was once cornered at an after party of a conference, in a bar, and somebody like who was way too drunk was like explaining to me in very loud, aggressive terms that the problem with NPM is that when it downloads the code from GitHub, it doesn't cache it. And I was like, there's several things wrong with this, but I, and it was like, no, you don't understand. I read between the lines. I'm like, okay. Pretty sure I wrote that code, but all right. I don't know. I don't feel bad sharing that story because there's zero chance he remembers it. Yeah, so another thing, again, like people have told me that package resolution, download, extraction, that it's not parallelized. And that writing to the file system is just inherently slow. You have to not write to the file system, which like, okay, but you need the code there. And also the biggest one, this is one that we hear again and again. Developers these days are bad, sloppy, bad people, especially JavaScript developers. They just all need to get better. So what are the real reasons? In fact, JavaScript is not the fastest language platform, but it is incredibly fast. And the bottleneck is almost never the runtime. Using many dependencies is actually the point of a good package manager. That's why you have a package manager, so that you can offload all this stuff to dependencies. That's actually a success state. That's not a bad thing. Every package manager, even the slow ones, they cache pretty much everything. Like, that's just the first thing you do. Not all caches are the same, though, which I'll get into a little bit. Every package manager parallelizes a lot, pretty much as it possibly can. And it is fair that writing to the file system is legitimately kind of slow, but they all minimize it and only write as much as they absolutely need to. And you just have to do that. There's no way around that. So, and yes, developers these days are in fact bad, sloppy, bad people, but not JavaScript developers. You all are the good ones. So there are some opportunities for improvement. Like I said, we do all parallelize the stuff that we do, but procrastination can be a lot better than parallelizing. A lot of y'all are putting way too much asynchrony in your JavaScript programs. When there's no parallelization benefit, asynchrony actually makes things go slower. There's a lot of deterministic CPU-intensive work which gets repeated again and again and again. For example, caching a gzipped artifact, and then you have to un-gzip it every time you read it from the cache. There's a lot of security paranoia, like checking integrity unnecessarily. You could argue that like security paranoia is better than security YOLO, but still, it's all, it is a performance loss. A lot of times there are hot paths that are not optimized, or optimized for like an old version of the engine, and then the engine changes and what was fast is now slow. And everybody except PNPM pretty much has this problem, but PNPM, this is like the big reason why everybody's using PNPM. Hierarchical resolution of dependencies is incredibly slow, and it's kind of unavoidable. Having a rat's nest of symlinks is actually way better. So in other words, this is my talk. No, we're not going to rewrite it in Rust or Zig. We're just going to do some real basic stuff, and I'll tell you what that stuff is. Before I get too into that, as you know, don't ever do performance updates without a benchmark to prove that it's actually better, but we need to have a talk about like what benchmarks are for in our industry. I'm not going to show you our benchmarks in this talk because I'm not here to pick a fight with anybody. I think it's good to benchmark like known hot paths for a given use case, but it should not ever really be a flex. When you see a benchmark presented as a like very beautiful graph in a blog post that's glowing with praise about how you should use this or that platform, like be super, super suspicious of it. A lot of times we see things where people are like, oh, well, this one function call is like 1,000,000 times faster than this other one. It's like, okay, well, if that's only 1% of your total time, 1,000,000 times improvement of 1% is a 1% improvement. Like, that's not necessarily a good use of effort. So yeah, identify your hot paths with profiling and then benchmark that. Another thing is don't be afraid to make a benchmark slower if it makes your overall performance better. So one example of this that we see a lot of times, that we've leveraged a lot of times in Volt actually, is like doing some work up front so that you don't have to do it multiple times on every instantiation or on every function call. And also speed is less important than reliability or correctness. So it is still pretty important to just test it after you validate actual tests. So another, this is an important wise quote I heard somebody say one time, which is that benchmarks should be a diagnostic tool and not a marketing flex. I think he put that really well. All right, so this is what we're doing at Volt. These are also hopefully some techniques that you can use in making your own node programs faster, or any programs faster, really. Like I said, procrastination is better than parallelization. So what does that mean exactly? A lot of times a program has a bunch of stuff it needs to do that doesn't really need to be done like with 100% reliability or right now. If you can kick that off until later with like a detached child process that will kind of like do its best and maybe die and maybe not, a lot of times that's actually the best way to do it. So we use this pretty heavily in two cases. One is we have a daemon process in Volt that will run through your cache and unzip everything in situ so that the next time you load it from cache, we don't have to ungzip it. And then we also do this for removing files because like if there's some extra files, as long as they've been moved out of the way in your node modules folder, like it's fine. You got plenty of disk. This is what it's doing for cache unzip. So you can see the actual method here that does the unzipping. There's this register method that just sort of creates a list of all the things it has put into the cache that were gzipped. And then it calls this handle before exit on the before exit event, which just spawns a child process in detached true mode and then writes all of these things into its standard input. The reason why we do this, why we write it into standard input is because if you have like, 10,000 of these files, like you can't put 10,000 paths in the argv or else it'll blow up. Yeah, and then we just unref it so that we can close whenever, and this will keep running. So like you think your install is done. It's not actually done yet. It's going to keep doing stuff until it's all the way done. Another one is excessive asynchrony. The worst offender here is fetch, which and this is actually a double whammy because you get the extra promise created, right? Because you need the promise for the result and then another promise for the body or whatever. Which if you're just going to consume the whole body, you could just be like, just tell me when you're all the way done. It's fine. The other thing is that there's a web stream underneath it for the fetch implementation, which also defers every single event that it does. And so there's just like this massive explosion of promises being created. But a lot of APIs actually provide like an async interface for Zalgo safety because you want things to be consistent, but then that ends up just deferring stuff unnecessarily. What I've always kind of said is like async IO is not a magic fast sauce you just pour all over your program. If you're not actually getting a parallelization benefit, async IO makes things slower because now there's extra overhead. Never repeat deterministic computation. This is that cache unzip thing that I showed you was an example of that. It's really common. I've noticed actually, we did this in NPM. I mean, I said I wouldn't make this like a 10 things I regret about NPM talk, but this is one thing I really regret about NPM. We made the cache a like very standards compliant web cache, right? If you wanted to take NPM's fetcher and use it as like a browser crawler, it would pretty much do exactly the right thing. And behave just like a web browser. But like, we're not a web browser. We don't need to behave just like a web browser. We can take all kinds of shortcuts because we know exactly what kinds of things we're downloading. So yeah, the JSON has to be gunzipped right away. There's no way around that. But the tarballs can be gunzipped later. So we procrastinate that. And then once we parse the JSON, we actually cache the V8 serialization of it so that the next time we need to load that same object, if it's a cache hit, we just dump it straight into memory. There's no deserialization involved. Also, we found in some cases, it's something worth exploring, like binary length prefixed key value strings might be a lot faster than JSON or text files. Just something to keep in mind as you're digging into this kind of thing. Security paranoia. So there's a tendency to say, aha, here is an identity or a signature, I must verify this. Especially this is really important if the bit integrity is your cache key. So it's it's tempting, and occasionally you can, if you construct benchmarks like in a very precise way, you can make it look like a content addressable cache is incredibly fast because you get the key for the thing and then, oh, the thing is there and I don't have to look it up again, and the key's not ever gonna change throughout the course of your benchmark because, hello world string is like gonna hash to the same thing every time. And you can say, aha, my web platform performs a bazillion times better because we're using a CA cache. And this is a little bit, so then that ends up in practice though being that you have to do a SHA-256 or SHA-512 hash of your object every single time you basically interact with the cache at all, and that can blow up your CPU. NPM, I know, spends a ton of CPU time just calculating these hashes over and over again. And in general, you don't want to trust outside input. That's kind of a basic principle of computer security, but your own program should not really be considered outside input most of the time because it's not outside. This also tends to show up a lot in redundant guarding against file system failures. File systems don't actually break that much. They're pretty good at storing files and retrieving them. Most of the time when you have a file system or like what looks like disk corruption, it's actually just that you had two processes writing to the same file at the same time. And you can solve that by just doing atomic writes and being really careful about that and save yourself a lot of, file checking because you can just trust the file system. So sometimes an expressive high-level language can actually lead you down this like garden path of really inefficient practices. So for example, it's really easy to let's say I want to find like the largest number in a list of numbers or the highest Semver version in a list of Semver versions, which is, because we're actually a package manager, that's what we're really doing. It's super easy to just sort the array because I have a sort function and then pick the top one. But actually that ends up doing a lot of extra work because I'm also sorting the third highest and the fourth highest and the fifth highest and making sure they're all in order. And I've got this n log n process happening when really I could have just passed through it once. So also, and we found this in particular with Volt because in a typical project install, you have 5 to 10,000 installed dependencies. And obviously some of those have hundreds of deps, some of them have 1 or 2, but the average is around 5 to 10 production deps per dependency, and around 10 to 50 published versions out there that we need to kind of pick the best one of. The result is you end up with many millions of Semver range tests per installation. We were just hitting that Semver satisfies over and over and over again. So normally micro-optimizing something, like I said, you did 1,000,000 times improvement of a 1% of your program. The typical NPM install, it would not be incorrect to say that it is mostly just doing Semver range checks. That's what it's spending all its time doing. So we did build a new Semver implementation and a new implementation of the pick manifest that kind of gets the pacument and then picks out which is the best one, specifically because of this. And what we found was the tweaks and the hacks and iteratively just running our benchmarks and trying to shave off another % here and there. We were doing that in V8, and then we tested it in Dino, and obviously it ran just as fast because Dino is also V8. And I was like, let me see. Oh, people talk about how fast Bun is. I tried to run it in Bun. It was 10 times slower than Node Semver. So yeah, be careful because those micro optimizations do tend to be very engine specific, and what's good in one might not be good in another. And the last one, like I said, this is not, this does not apply to PNPM. We actually kind of got the idea from PNPM, although ironically, PNPM's approach is kind of similar to NPM 0.1 and 0.2 before NPM 1.0 started hierarchically nesting everything. But what we did, we ended up, it was sort of a case of convergent evolution. We ended up doing this thing where we have a dependency ID, what we call a dep ID. And that's just a deterministic identifier for a fully resolved dependency. So if you get the same dep ID, that means that it's the same dependency. You can just like, your deduplication is built right into that. And it also means that the lock file, the in-memory graph, the on-disk reification, they're all just representations of that same conceptual graph object. So it's a lot less work because now you don't have to consider hoisting, you don't have to kind of consider deduplication or a bunch of other things that are a really big hassle when you have nested dependency trees. So I think the kind of lesson, the takeaway here is you can often find the biggest performance win by kind of zooming out and looking at your data structure and going like, is there a better way to represent this thing? The reason why we always kind of held back from this approach with NPM was just largely because it was like, well, yeah, but people need to be able to like reason about what's in their node modules folder, and like raise your hand if you've ever reasoned about what's in your node modules folder. All right, so it's not even everybody at NodeConf. Not relevant. It was like, just for posterity, it was like half the people here raised their hand. So, you know, but y'all are like the nerds about this. Like, how much do you think like other people out there are doing it? Like 0. So just make the rat's nest of symlinks is fine. So what this ends up looking like, I have had some conversations here and also like in the past about lock file surgery. I don't recommend performing lock file surgery unless you are a trained surgeon of lock files. But this is kind of what the graph looks like in Volt. We have just this array of nodes, and then there's another section which has, you know, what are the edges that are linking between them, and we know how to reify that, and we know kind of what that means. And this has exactly those same dep IDs as the folder name, so it's all completely deterministic. Now this like looks intimidating and dense and weird, but the nice thing about it is then the diffs are super, super straightforward. So, you know, in the diff, you can just be like, aha, I see that this thing went from 310 to 311. Whereas the diffs in a nested type of structure end up being like, well, this thing went from having like 4 indentations to only 2. What does that mean? So yeah, that's one thing I think has been, and it does have some performance impacts because, like I said, we don't have to consider hoisting or shadowing or deduplication or any of that. So yeah, try it out. It's pretty good, but it's still very, very early. There's a lot yet to do. The UX has something to be desired in terms of like how it reports errors. It's just like, there was an error. Here's a giant error. Here's a giant stack trace. And there's a ton of stuff that didn't fit into this talk. And so there's going to be a Volt workshop, I believe, at 2:30 or something later on today. It's at 4. 4 o'clock, yes. And like, for example, we have this really cool way to explore your project's dependencies, which I just think is rad. You can also come and find us at volt.sh, or we have a discord.gg/volt package. Yeah, and hope to see you all soon.